Our agenda today, we're going to cover natural frequencies, sinusoidal input, transient inputs, random vibration inputs, and then there's the response spectrum and the DDAM analysis type. So first off, we're going to talk about natural frequencies. Normal modes, for example, are also referred to as a modal analysis, will determine the natural frequencies of a model. And we use this to inform, you can basically use this to inform your design, but keep in mind that a modal analysis will provide displacement and stress results, and these results are not real results, they're normalized results. So the modes and the mode shape are most important that we can get out of a modal analysis. But also that the modal analysis is our basis or starting point for a lot of the other types of dynamic analysis. So next up, we have sinusoidal input. Sorry, keep pushing the wrong buttons here. So frequency response is the simulation of the peak response from a steady state sinusoidal input. So the easiest way to describe this is think of a shaker table, but digital. It does exactly what a shaker table does for most part. There are two methods. There is the direct integration and modal superposition, but we'll talk about those differences later on. So examples of this would be anything you would put on a shaker table is what you can simulate, but the structures supporting motors or rotating shafts, agitators, for example, or anything attached to these structures are something that you can look at with the frequency response. It is, like I said, it is the response. It's your peak response to a steady state sinusoidal input. So next up, we have transient analysis. We have nonlinear and linear transient. The easiest way to describe this is that it is a march through time. We're taking incremental time steps as we solve a ever-changing or a time-based load. You can think of it as a brute force, but technically you can simulate for the most part all the other dynamic methods because we are simply marching through time. Problem with this though is it's very expensive and it can take a very long time to solve for longer duration simulation, so it's best for short duration events. So imagine that we're taking like 1/10 of a second each increment, and we need to solve for an event that takes like 5 minutes to solve. Not only do we have the iterations to converge for each increment, we also have every increment to go through, so that becomes a lot of solving. But also something to keep in mind is that even though this is a transient and we're looking at transient situations, it can't simulate very fast occurring situations because we are limited by that of the implicit solver. So things like a high-speed impact or ballistics are going to exceed the limitations of our transient analysis. There is the nonlinear versus the linear transient. The same differences the differences are similar to that of a static analysis. So the same differences are as a static analysis, for example. So we've got our small versus large deformation, our follower forces, or even just nonlinear material. We can't use those in the linear analysis, but we can use those in the various nonlinear approaches. Also, something to keep in mind is that a linear doesn't track, it's not looking at displacement work or load convergence. So as it marches through time, your results can end up being time step size dependent. So that's just another thing that you'll have to be concerned about in a linear transient analysis. So we've got next is the modal versus direct integration comparison. The modal is less computationally intense, but that is only if there is modal damping. Any other additional damping effects will slow down the analysis to the point where it's more comparable to a direct integration. There are some other minor issues that you can run into with the modal superposition, and that is that if you underestimate the number of modes that you solve for initially, then you won't get the full application of any sort of important frequencies when you do perform the transient aspect or the frequency response, for example. And then the others, on the inverse of that, there is overestimating the number of modes. There is no negative impact to your results, just that it slows down the analysis as more of those modes are used in the computation of the response. Another advantage of the direct is that you can get some additional nonlinearities in your analysis. That is the discrete damping and frequency-dependent damping, along with frequency-dependent stiffnesses. So that brings us on to our 401, 402 multi-step solvers. These solvers have a much improved contact modeling for better accuracy. And along with that, we've got sequential or independent subcases. And with those multiple subcases, you can have different contact pairs active or inactive between the subcases, and you can even use different analysis types between subcases. So you might have your first subcase be a static analysis, so that you get your pre-stressed model that then has a dynamic event applied to it. But also, in addition to that, we get some additional nonlinear materials to work with, such as cohesive elements, ply failure, and some additional hyperelastic materials. Though keep in mind that the 401, 402 multi-step solvers do require additional licensing for. So that brings us on to some examples of transient analysis. There are, as transient as it sounds like, it's basically anytime you have a time varying load, such as an impulse or a shock load, for example. And in my little picture on the upper right there of that could be anything from like a displacement versus time or acceleration versus time. As you can see, it varies across the plot. But in my example here, it's rather a poor example, as this is a very noisy input signal, and such we might prefer to do a different analysis type on that. But another analysis type that's most common would be like an impact or drop test analysis. Phones, we drop those all the time. So that was, to me, a perfect example of why you might want to perform an impact analysis. Is if you're dealing with a consumable product, a consumer product that is handheld and that can be easily dropped. Next, we get into random vibration. As you can see here from the input here, we've got a lot of overlapping signals with each other, so much so that we can't quite identify the different inputs here. And so in this situation, we have a random vibration. Random vibrations are used for when our loading conditions are noisy and it obscures the real signal. So instead of a direct approach, we take a probability analysis on this. And so your input is going to be in the form of a power spectral density function, or also called an acceleration spectral density function. And this data, or this input, is technically a statistical analysis of that noisy signal. The units are going to be a bit unique in that they're going to be a root mean square of acceleration. Usually you'll see it as g squared per hertz on the y-axis versus frequency on the x-axis. And then these results that we'll get from this type of simulation will be given in the form of 1 sigma of the probable response. So keep that in mind in determining the probability of our max stresses and displacements that will occur based off of this input signal. So situations in which we might want to use this random vibration would be a rocket. Rockets generate a lot of energy, have a lot of moving parts. Well, not necessarily moving parts, but there's a lot of parts generating movement. And these overlapping signals will cause the input signals to be too noisy, and so therefore we'll take more of a statistical approach to it. Also, turbulence, anything like that, those are irregular, so they is usually taken in a statistical format. Same thing with road noises for an automobile cruising along a very pothole-ridden road like this. Obviously, we can't quite simulate the event because the entire event might be minutes, hours, or whatever. So what we'll do is you'll take a sample of that and we'll convert that to a power spectral density function. And then one of the more obvious examples of a random vibration is earthquake. As you can see here in our lower right-hand image, we've got a seismograph here, and we've got our acceleration versus time. And it's a very noisy input signal, and the time step size required to capture that sort of event would be very small for a very long duration, which will slow down our analysis significantly. And also, this is also just a sample of a specific earthquake. Multiple earthquakes will have, or different earthquake, or the earthquake isn't always exactly the same sort of acceleration over time. So that's why the statistical approaches are used for it. And that over on our left-hand side is a graph demonstrating what a PSD input will look like. It is usually in the log format here, as you can see. Next is our response spectrum. This is kind of specific to the analysis of a small system in a larger structure. For example, that would be like equipment in buildings. You do require the response of the larger structure for the input. This isn't something you're just going to simulate straight out of the box. So you're going to need that input of that larger structure. That input usually is in the units of acceleration versus frequency. So meters per second squared, or in terms of G versus your each frequency. But this is always determined from the larger structure analysis. Some building codes may still require this particular analysis type, for example, nuclear applications. But I suspect most of us here are probably mechanical engineers, and this may not be up your alley, but this is more of a structural analysis for civil engineers. And then next we've got our dynamic design analysis method, also called the DDAM analysis. The DDAM is specific to shock loading for explosions. It's developed by the U.S. Navy and is required, as far as I understand, for all their naval applications. It's very similar in the sense that the way the response spectrum works, in that you're solving for equipment in a larger structure, but in this case, the structure is a surface ship. The loading conditions are a bit more straightforward. We don't necessarily have to know the dynamics of the ship itself, because these are more intrinsic to the solver, and they're based more on where the equipment is located. So you'll be selecting something like it's located on the deck, or attached to the superstructure, or something along those lines, making it a little bit more straightforward in setting up. So that kind of brings us here to the end of our presentation here, at least of the different dynamic simulations. As you can see, we are capable of simulating a variety of different dynamic events, and there are a few or a couple of specialized tools that are better tasked for more specific sets of analysis, such as our frequency response for a steady state input, and our random vibration for noisy inputs. So this was a brief overview, but you can find some additional information on our YouTube channel at Saratech Inc. There is the Simcenter Femap Intro to Dynamics, where we go into more depth for the modal analysis, frequency response, and a random vibration. And we also offer some online or on-site training. The Femap 501 Dynamics course will cover in much more detail the dynamics of in translating our dynamics to simulation, from single degree freedom to multi-degree freedom analysis.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.